Bracket is a very useful and powerful technique in classical mechanics. It gives the geometrical structure of phase space transformation. It provides the link between the classical mechanics with quantum mechanics. In our previous module, we have discussed Lagrange bracket and Poisson brackets and their properties. Now, using the Poisson bracket, we shall search different constants of motion. In this module, we shall search for constants of motion. Next, we shall find the condition for canonicality using brackets. Then, Hamilton-Jacobi equation will be discussed. Now, constants of motion. By a constant of motion, we mean a function in the phase space which is independent of time and whose value is constant for any particle or point. Let capital F, function of small qi and pi in the phase space, it will be a constant of motion if ddt of capital F equal to 0. ddt of capital F means the total time derivative of capital F, which gives first order partial derivative of capital F with respect to small t plus Poisson bracket of capital F with Hamiltonian capital H equal to 0. Since capital F, function of small qi, small pi does not depend explicitly on time t, so we have first order partial derivative of capital F with respect to small t vanishes. Thus, using this we get Poisson bracket of capital F with Hamiltonian capital H equal to 0. So, one can say that if capital F, function of small qi, small pi is a constant of motion, if we have Poisson bracket of capital F with Hamiltonian vanishes. Let us check the other constants of motion. We shall use the result that if capital F1, capital F2 be two constants of motion, then their Poisson bracket capital F1 with capital F2 is also a constant of motion. The time derivative of Poisson bracket capital F1 with capital F2 gives the time derivative of first order partial derivative of capital F1 with respect to small q into first order partial derivative of capital F2 with respect to small p minus first order partial derivative of capital F1 with respect to small p into first order partial derivative of capital F2 with respect to small q. In this line, we have just used the definition of Poisson bracket of capital F1 with capital F2. Then, taking the derivative, we get 4 terms and those 4 terms are written within the third bracket in the next 2 lines. In next 2 lines, we have used the result that order of differentiation can be interchanged. Changing the order of differentiation, we have written those 4 terms here and we have arranged the terms in a useful manner so that these 2 terms can be put like this and these 2 terms can be put like this. These 2 terms can be combined as the Poisson bracket of first order ordinary derivative of capital F1 with respect to time t with capital F2 plus Poisson bracket of capital F1 with the first order ordinary derivative of capital F2 with respect to time t. Please note that here we have used that the DDT operation and del del q or del del p can be interchanged. If capital F1 and capital F2 be two constants of motion, then they are independent of time. So, we have ddt of capital F1 equal to 0 and ddt of capital F2 equal to 0. Therefore, we have ddt of Poisson bracket of capital F1 with capital F2 vanishes. From this, one can say that Poisson bracket of capital F1 with capital F2 is a constant of motion. We shall use this result in searching the constants of motion. First of all, consider the linear momentum. If we put capital F equal to small p in the previous result, where small p is the generalized momenta conjugate to the generalized coordinate small q, then we have ddt of small p is equal to first order partial derivative of small p with respect to time plus Poisson bracket of small p with Hamiltonian capital H. As small p is independent of time, so we have del del t of small p equal to 0, that is first order partial derivative of generalized momenta vanishes, which gives the ddt of small p equal to Poisson bracket of small p with Hamiltonian. Now, from Hamilton's equations of motion, we have Poisson bracket of small p with Hamiltonian is equal to minus first order partial derivative of Hamiltonian with respect to small q. If small q is a cyclic coordinate, then Hamiltonian capital H does not contain q explicitly. So, del del small q of capital H vanishes. Using this result, we get Poisson bracket of small p with Hamiltonian equal to 0. Therefore, ddt of small p equal to 0. Hence, linear momentum small p conjugate to a cyclic coordinate small q is a constant of motion. Next, we shall discuss about angular momentum. Let capital Lx, capital Ly, capital Lz denote the components of the angular momentum vector capital L vector along the coordinate axis respectively. We know that angular momentum is the moment of linear momentum. Therefore, we have capital Lx equal to small y into small pz minus small z into small py. Small pz means the component of linear momentum along z axis. Similarly, others. Capital Ly equal to small z into small p suffix x minus small x into small p suffix z, capital L suffix z equal to small x into small p suffix y minus small y into small p suffix x. Now, the Poisson bracket of capital Lx with capital Ly, we have written the value of Lx and Ly already obtained, and putting these value we get the result which have been written in the right hand side of this line. Then we have separated the terms using the property of Poisson bracket. Then again we have used the property of Poisson bracket and we get these results, which is nothing but the component of angular momentum along z axis, that is capital L suffix z. Please note that other terms vanishes. This term vanishes since we have proved that Poisson bracket of capital F1 with capital F1 vanishes. Similarly, other. One can obtain the results this one and this one in a similar way. If capital Lx and capital Ly are constants of motion, then their Poisson bracket is also a constant of motion. So, Poisson bracket of Lx with Ly is equal to Lz, L suffix z is a constant of motion. Therefore, the angular momentum vector, which is capital L vector, can be written as capital L suffix x I vector plus capital L suffix y j vector plus capital L suffix z k vector is also a constant of motion. Now consider energy. If we set capital F equal to Hamiltonian H, then we have ddt of capital H equal to first order partial derivative of capital H with respect to time t plus Poisson bracket of Hamiltonian with itself. If capital H does not depend on time t explicitly, then we have del t of capital H equal to 0. Moreover, from the property of Poisson brackets, we have Poisson bracket of capital H with capital H vanishes. Hence, ddt of capital H equal to 0. This proves that Hamiltonian capital H is a constant of motion if it is time independent. It is already proved that Hamiltonian H represents the total energy of the system. We have discussed about it in chapter 4. Therefore, the total energy is a constant of motion if the Hamiltonian does not depend on time explicitly. Let us find the condition for canonicality. Here we shall use the Poisson bracket in searching the condition for canonicality. The condition of canonicality can also be expressed in terms of Poisson bracket. Evaluation of Poisson bracket is very much convenient for practical purpose. So, let us try to find the condition of canonicality in terms of it. In a canonical transformation, small q, small p and t transforms to capital Q, capital P and t. The same time parameter t occur in both the phase spaces spanned by small q and small p and capital Q and capital P. Small q is the generalized coordinate, whereas small p is the generalized momenta. These are in old coordinate system, whereas capital Q, capital P are in new coordinate system. This helps us to test the condition of canonicality in terms of small q, small p, capital Q, capital P, and also with their time derivatives. Let us consider the condition of canonicality already obtained and given by summation over I equal to 1 to n small pi into delta small qi minus capital Pi into delta capital Qi equal to delta capital 1, which is an exact differential. Here delta means we are not considering the change in time. Here the parameter t is held constant. In capital Qi, function of small q, small p, t, capital Pi, which is a function of small q, small p and t, and capital F1, this is a generating function which is a function of small q, capital Q and t, while finding the differentials delta small qi, delta capital Qi and delta capital F1. A necessary and sufficient condition for a transformation capital Qi equal to capital Qi function of small q, small p and t, capital Pi equal to capital Pi function of small q, small p and t for I equal to 1, 2 up to n to be canonical transformation for fixed value of time t. Now, the left hand side of the above condition can be expressed as follows. Summation over I equal to 1 to n small pi into delta small qi minus capital Pi into delta capital Qi. In the right hand side, we have separated these two terms and written in the right hand side of first line. Then in the next line, first term has been written as it is, and say in case of second term, we have replaced delta capital Qi as summation over j equal to 1 to n del small qj of capital Qj into delta qj plus del small pj of capital Qi into delta pj, since capital Qi are functions of small qj and small pj. Then we have adjusted those terms, and adjusting those terms we have keep it in this form. This expression will be perfect differential if this can be written in this way, that is first order partial derivative of small pj minus summation over I equal to 1 to n capital Pi into del small qj of capital Qi with small qk equal to del small qj of small pk minus summation over I equal to 1 to n capital Pi del small qk of capital Qi. On simplification, these can be written as this, that is del small pk of summation I equal to 1 to n capital Pi del small pj of capital Qi equal to del small pj of summation over I equal to 1 to n capital Pi del small pk of capital Qi, and del small pk of small pj minus summation I equal to 1 to n capital Pi del small qj of capital Qi equal to del small qj summation over I equal to 1 to n capital Pi into del del small pk of capital Qi. Here small qi and small pi are independent variables. Therefore, the above conditions can easily be shown to reduce in terms of Poisson bracket, as Poisson bracket of small qj with small qk equal to 0, Poisson bracket of small pj small pk equal to 0, Poisson bracket of small qj small pk equal to Konecker delta jk. We have already defined Konecker delta jk, which is Konecker delta jk equal to 1 for j equal to k, for j not equal to k it vanishes. This gives the necessary and sufficient condition for the condition for canonicality of a transformation. If one uses the inverse transformation and proceeds in the same way as above, then the condition for canonicality can be obtained as, instead of small q, we shall get the result after replacing small q by capital Q. We get this result after replacing small p by capital P. In this result, after replacing small q by capital Q and small p by capital P, we get this result. Remarks: knowledge of Hamiltonian is not needed to judge the canonicality of a given transformation. Moreover, any specific property of a dynamical system is not needed for this purpose. The system must be holonomic, and we have the number of degrees of freedom of that system. So far, we have discussed the detail about Poisson bracket. It is a very useful technique. The condition for canonicality can be obtained in terms of Poisson bracket. It is very important in searching the condition for canonicality and testing some phase space transformation whether they are canonical or not. Now we shall test some problems for canonicality. Now let us solve some problems. First problem: show that the following transformation is canonical. Capital P equal to half of small p square plus small q square, capital Q equal to tan inverse small q divided by small p. The given transformation will be canonical if Poisson bracket of capital Q with capital P equal to 1, Poisson bracket of capital Q with capital Q equal to 0, Poisson bracket of capital P with capital P equal to 0. Now let us find the partial derivative of capital P with respect to small q, which gives small q, whereas the partial derivative of capital P with respect to small p gives small p. We have calculated these from these relations. Now we are finding the partial derivative of capital Q with respect to small q, which gives this, and calculating the partial derivative of capital Q with respect to small p, we get this. Q has been given here. Now Poisson bracket of capital Q with capital P is defined as this. Using this value already obtained, we get after simplification that Poisson bracket of capital Q with P is equal to 1. So the transformation is canonical. Let us consider problem 2. Find the values of alpha and beta for which the equation capital Q equal to small q to the power alpha into cos beta into p, capital P equal to small q to the power alpha sin beta into p represents a canonical transformation. We know that the transformation will be canonical if it satisfies these results. Now, let us test. Poisson bracket of capital Q with capital P can be defined as this. Now, as capital Q and capital P have been given here, so one can calculate these partial derivative, that is partial derivative of capital Q with respect to small q, which has been given here, and the partial derivative of capital Q with respect to small p, which is this, and the partial derivative of capital P with respect to small p, this has been written here. The partial derivative of capital P with respect to small q, it has been written here. After simplification, we can combine the result like this. Since sin square beta plus cos square beta equal to 1, so we have this result. Sin square beta p plus cos square beta p equal to 1, so we get this. So, the transformation is canonical if alpha into beta into q to the power 2 alpha minus 1 equal to 1. From this relation, one can get alpha beta equal to 1 and 2 alpha minus 1 equal to 0, since q to the power 0 gives 1. From these two relations, if we calculate, then we get alpha equal to half and beta equal to 2. Now, we shall discuss one important equation, Hamilton-Jacobi equation. Consider a canonical transformation from the coordinates and momenta small q and p at the time t to a new set of constant quantities, which are small q0 and small p0. The initial values at t equal to 0 of small q and small p, that is q0 is the initial value of small q, whereas small p0 is the initial value of small p. For this, the transformation relating the old and the new canonical variables represents the solution of the problem, which can be written as small q equal to small q function of q0, p0 and t, small p which is a function of small p function of small q0, small p0, t. Since the new set of canonical variables are constant in time, so the transformed Hamiltonian capital K must be identically 0. The equations of motion are capital Q dot equal to first order partial derivative of capital K with respect to capital Pi, which vanishes, and capital P dot equal to first order partial derivative of capital K with respect to capital Qi with a negative sign, which is 0, where capital K is the transformed Hamiltonian is equal to Hamiltonian plus del t of capital F. If capital K vanishes identically, then we have right hand side equal to 0. Let us take the generating function capital F as function of the old coordinate small qi, new constant momenta capital Pi and time t. That is, if we take capital F2 is a function of small q, capital P and t, then small pi is given by this relation. Hence, capital H, which was a function of small q1, small q2 up to small qn and small p1, small p2 up to small pn and t, then putting these value for pi, we get that Hamiltonian is a function of these plus del t of capital F2 equal to 0. This equation is known as Hamilton-Jacobi equation for the generating function capital F2. Poisson bracket is basically a mapping of two dynamical variables in a phase space transformation. It is very helpful in Hamiltonian system. Using Poisson bracket, we can get the condition for canonicality. In such cases, the knowledge of Hamiltonian does not needed. In this module, we have discussed the detail about it. Hamilton's Jacobi equation, which plays an important role, has also been discussed.